Without further ado, it's my pleasure to introduce Dr. Christopher Rackauckas. Dr. Christopher Rackauckas is co-PI of the Julia Lab at MIT. His research focuses on scientific machine learning. He's the lead developer of the SciML organization, which is an incredibly high quality, very complete collection of tools for scientific computing, everything from super high level modeling languages all the way to low level kind of specialized numerical algorithms, and importantly, all the stuff in between too. So it's really amazing collection of software. He's also lead developer at Pumice AI, bringing these techniques to pharmacology, at Dyad, addressing massive problems that arise in hardware design and industry. I can go on and on and on about his contributions and his impact. The vision and execution is truly unmatched, and so we're thrilled to have you give a talk for the class today. With that, the floor is yours.
All right, thank you. Thank you for the introduction. Yeah, so today what I want to talk about is, I guess it's kicking off the new module, right, on scientific machine learning and all the different things about that. So I want to kick it off with the, kind of approach that is really mixing in the classical solvers, and we can also have a larger discussion as to why this approach and a lot of the motivations behind it. And feel free to interrupt me at any time. I'll be pretty fluid with how we go back and forth here. And if I have enough time, I'll also do a full derivation of the adjoint method. I have it planned, but it turns out that kind of takes a while sometimes. So I might end up just linking to that derivation in my course notes if it takes too long. So okay, but so basically the core idea here, and what we're going to really build up is this idea of scientific machine learning, which is model-based data efficient machine learning, right? And the way that you get this to be model-based or data efficient is to basically combine the two worlds, right? There's a few different ways to be able to think about this and motivate it. One way to think about it is, you have a lot of scientific knowledge, right? So, you know how chemistry works, you know how biology works, you know how a lot of physics works, right? So why are you trying to train an AI model completely from data if you already know how something works, right? You should basically be only making it learn the things you didn't know, right? That's a high level kind of description. I think, as another way to describe it is the fact that a lot of scientific knowledge is actually built from heterogeneous data, and that is very different from the data that you use in machine learning, right? One way to understand this is, for example, take general relativity, right? If you think about general relativity, if I was to ask you, why do we know that general relativity is true? You'd say, well, it's been scientifically verified. Like how has it been scientifically verified, right? There's some data for that, right? Could you train a neural network to just know general relativity, right? And the answer would be kind of difficult to find an actual data set to do that, right? And why is that? Well, because the way that we know general relativity is true is because we've observed, when gravitational lensing out in the deep in deep space, right? We've observed from eclipses that we can see that how much the stars move, and that gives you a gravitational lensing effect that is very predictable, right? We know from the perihedron of Mercury, right, that the way that Mercury moves is not actually a Newtonian two-body problem. It has a different physics to it, and that was one of the main predictions and proofs from general relativity, right? We know from satellites that we put up into space that there's a time dilation that has to be accounted for. Otherwise, GPS would be incorrect, right? I mean, so we know a whole lot of different things that basically all point us to be saying at least general relativity, maybe if it's not true, it's at least very, 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 very close to true, right? But there's no single 3 billion row, Google data set that you would be able to put to a machine learning process and then just say, hey, here's my inputs, here's my outputs, learn general relativity, right? And so the interesting thing about models and basically science is that this is encapsulation of a lot of heterogeneous information, right? So when if another thing, a way to think about this is, for example, the things that we know about chemical processes, right? Each one of these arrows of this chemical combined with this one, they could even be different papers or different PhD theses in the past. Used to just be, I proved that these two chemicals actually bind with each other, right? So every single one of these arrows, there's a different scientific experiment and a different, written in a different language with a different way of being measured and everything, right? But who cares about all that? We know the scientific model, so we can make predictions from it, right? And the idea here is that if we can use this information that's embedded in models and compensate this with data, then maybe we can make better predictions than any of them alone, right? Because data, in machine learning and what we call AI is really about, dealing with really big homogeneous data sets, right? The corpus of the English language in Wikipedia or on the internet, right? It's just one gigantic string, effectively, right? Where you just have, you have arrays of strings for each website, right? And these are things that machine learning is very good at learning from and predicting from. So the real question is, can we build predictive systems that are using this kind of homogeneous data machine learning approach with the with the machine learning, with the scientific modeling approach that we've done as well. Right? And so here's one technique to be able to achieve this, is the universal approximator differential equations. And the idea behind these is to use neural networks not as a model of the brain or whatever Sam Altman likes to say about neural networks, right? The whole point that we want to use neural networks for is we want to use them as a function approximator. And now let me actually change my screen share here so that way I can go back and forth to a I guess you're just going to get my entire screen here, and I'm just going to make sure I close a few things. And so okay, so can you see my screen here?
Yes.
Yeah, so let me just kind of, if I had a whiteboard, I'd whiteboard this, but I'll do the equivalent online version, right? So what is a neural network, right? So a neural network is it's a function which satisfies universal approximation, right? So what do I mean that? So here's your very standard neural network. A neural network is let's say we take in a vector x, right? What we're going to do is we're going to apply a matrix to it. So this is just a matrix vector multiplication where W is some matrix of weights, right? What we're going to do then is we're going to add a bias to it. This is just some vector of weights, right? Then we're going to do some sigma, some nonlinear operation around this, right? This is normally something like a tan h. So let's just say that sigma is equal to something like tan h, or it's something like a sigmoid, right? It's some kind of nonlinear function. Effectively, it needs to be nonlinear actually for the proofs to work out. Oops. And so what do we do after this, right? We do like, W2 is a matrix. So what comes out of this is a matrix times a vector. So you get a vector, matrix times a vector, you get a vector. Then this is some nonlinear function applied to the vector, right? Now, generally, it's going to be element-wise. So if we're in Julia, we'd actually have syntax for this. In math, we don't, right? But think about this as you apply some nonlinearity to each element, and then what do? Well, you get a vector out of here. So then you do a matrix vector multiplication. You do the same thing, right? I do another matrix vector multiplication. I add another vector. I do another nonlinear operation, right? Yada, 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 right? So this can keep on being repeated where you do the same idea over and over and over until you say, you know what, this is the last matrix I have. And then this is the last vector that I have. And now this is my neural network. This is my function, right? And so this is truly a neural network, right? This is your multi-layer perceptron piece, right? I hate all the silly pictures and everything because it kind of obscures the fact that this is just a mathematical function, right? That's all it is. This is not a approximation of the brain or whatever people are trying to sell you, right? It's just this is a function. A lot of matrix vector multiplications and there's a lot of nonlinearities, right? So, okay, why is this an interesting object to work with, right? The reason why it's an interesting object to work with is the universal approximation theorem, right? Also abbreviated a lot as the UAT. And then what this is basically saying is for every function for every function f in some function space, I'll call f, right? So think about f as like, f is equal to continuous functions or the space of, nice functions, maybe differentiable, yada, 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 right? So some space of nice functions. I'm not going to define it rigorously because, well, that's what your math class is for. And you kind of need all the PDE, Sobolev theory stuff. Who cares though, right? But it's a space of nice functions, right? So for every function f in there, there exists a set of weights. So there exists a W1, or I'll just say Wi, Bi, such that for all x in some domain where this needs to be compact, right? You need to have that there's some space that is confined in. So for all x in some domain, you have that the neural network of x minus f of x, right? If you take the norm between this, is less than epsilon. Yeah, so I forgot it. For all epsilon greater than 0, for every function, right? So, okay, this is not the rigorous statement because you need to be more rigorous about what this function space f is and certain details like that, right? But this is the understanding of the universal approximation theorem, right? So let's say there's a certain accuracy you want and a certain function, right? So you want to act like the function f and you want to be this close to it, right? There exists weights such that you can get that close to it, right? And you might ask the question of like, oh, how can you always, how can you always do this, right? And the real trick to it kind of comes from the fact that you have these different layers, right? Because so let's say you have a vector of 3 things that comes in, right? If W1 is 4 by 3, then W1x is a length 4 vector, right? But if I say that this is n, so if it's an n by 3 then it's an n, so you might have only 3 values come in, but after this, now you have this gigantic vector. You can make it any size you want. Now it's n, right? And then you can do this again. So you can, then you can say, okay, if W2 is m by n, then then when you get to this spot, when you get to this spot of the function, right, is a length m vector, right? And then suddenly also at the end, you then choose that W3 is k by m, then is a length k vector, right? And so the key is if I want n of x to be a function that is from math BB Rn, right arrow, math BB Rk, I just need to choose sizes, right? I just need to choose sizes n, m, and k, right? Where those are arbitrary. Well, right, but notice that m is arbitrary, right? Right. You need to have if you're trying to go from this size to this size, right? The first matrix, its number of rows is fixed because you need to be the same as your input, right? And the last one you need to be the same as the number of outputs, right? So that fixes the number of columns there, right? But as long as you have a few of these values fixed, you have some pieces in the middle that are that are actually resizable, right? So basically what you're doing is you're doing a linear transform. You're saying, I'm going to take a low dimensional object and I'm going to put it into a very high dimensional space. And then in a high dimensional space, I'm going to do operations on it. And I'm going to shrink it back down. And what the universal approximation theorem is telling you is that there exists an m, right? So I'm missing this. So a size of the hidden layers such that there exists weights, right? Because if you choose m to be big enough, then you get more and more weights. You can get infinitely many weights as you want, right? But basically, what this is telling you is that you can take a low dimensional thing and you can blow it up into a high dimensional thing, and then start to do different operations on all those different parts, right? So you can say, well, here's my low dimensional thing, but take the sine of the first part and take the cosine of it, and you can have many different ways of looking at that vector, and then you scrunch it back down. And then the idea is if you allow yourself enough ways to play with a vector where you're playing with each of the pieces individually, sooner or later, this can be something that can act like any possible function, which at a certain level, that should start to make sense, right? So this is the universal approximation theorem. And now, why is this important or interesting, right? Well, the reason why this is interesting then is that neural networks are then an approximator for any possible function, right? You basically just say, hey, I want to learn a function. What I do is I just define this mathematical object, right? I define this one mathematical object. And then as long as I can find the weights of this neural network, then I can guarantee that it could be close enough, right? Now the big question is, how do I find m? Right. Well, that's you use a process called well, the way that you find the weights is called gradient, stochastic gradient descent. Right. The way how do you choose m? That process is known as graduate student descent, right? Where a graduate student needs to try one value, another value, till it works, right? You're guaranteed that if you make it large enough, your neural network will work, right? You're guaranteed that that if that's large enough, you will find a value that will work, and that's really all that you know. But as long as your neural network is big enough, it can approximate any possible function, right? So this is how we understand machine learning. Machine learning is a set of tools that gives us the ability to learn functions really well, right? And now the question that you might instantly have is, why would you use neural networks as your tool for this, right? So here, don't you have other tools for this, right? So you have something like, t of x, which is, like a0 plus a1x plus a2 x squared plus dot, 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 right? This is your Taylor series expansion, right? You know that any analytical function, this is a universal approximator for, right? So you have a lot of other universal approximators that you've heard of, right? You also have that f of x. So you have let's call f of x equal to a0 plus sine of x, a1 sine x plus a2 sine sine of 2x, right? This is the Fourier sine series, right? So this is the Fourier sine series. So this is an universal approximator for all odd functions, right? If I remember correctly, yeah, for all odd functions, right? You need or I think that you also need that these are all continuous odd functions, right? But yeah, so this is also a Fourier series is also a universal approximator, right? So why is this universal approximator interesting, right? Well, the reason why is that these that I wrote right here, these are one-dimensional, right? I'm implicitly saying x is a scalar. So what happens if I have, say, for example, a Taylor series of x and y, right? Well, you can write down a Taylor series in 2 dimensions, right? You've done this probably in your analysis course. So you have like, a0 plus a1 a1x plus a2x squared plus dot, 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 dot. And then what you do is you do this in y2, right? You do b0, b1, y plus b2, y squared, oops, plus dot, 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 dot. But you actually need to, if you actually, that only works for isotropic functions. You actually have other terms you need to have in here, right? So you have to also have this, like a11, which is xy, and then you also, let's say we go to the next order, you have to have a21, x squared y, and a12, which is, xy squared, right? And you can see here that what you need to do is you need to do every combination of x's and y's together, right? And so the number of terms is order is O choose D, where D is the number of dimensions, right? And the crazy thing that begins to happen then is that as the number of dimensions increases, the number of terms required to build a universal approximator grows exponentially, right? Because if you think about it, like you have this, if you want to bring this out to say if you want cubic polynomials with 1,000 dimensions, then you need to do 1,000 choose 3 objects, and you can calculate pretty quickly, right? Like you can start to go, okay, let's go to Wolfram alpha. So Wolfram alpha, if I do like 1,000 choose 3 or something, right? You'll see that this gives you that you need 1 times 10 to the 8th number of terms in order to do a cubic polynomial, right? And you're like, well, cubic's not actually accurate enough. You're like, yeah, but you're never getting beyond that, right? So if you wanted to do cubic polynomials with 1,000 input dimensions, then the number of parameters that you need is 166 million, and you cannot do any less, right? So the key thing about neural networks, the reason why neural networks are used is that neural networks. So this is the curse of dimensionality. Using tensor products of one-dimensional universal approximators, right? So if you use a universal approximator that's a one-dimensional object, and you just take the tensor product between them in order to turn it into a higher dimensional one, this will naturally grow exponentially in the number of terms required to do the approximation as the dimension input dimension grows, right? And so neural networks solve the curse of dimensionality, which basically just means they are universal approximators where they have a polynomial growth cost with respect to the input size, right? And that's the key. You could use Taylor series if you have a small dimensional input. You could use a Fourier sine series if you have a small dimensional input. But neural networks are an object such that if you have very high dimensional inputs, you can get universal approximators that only have polynomial growth in the number of terms, right? So that's a neural network, right? That's, if you hear Sam Altman telling you neural networks are representation of the brain, no, give them this, go learn the proof of the universal approximation theorem and pull out a whiteboard right in front of them and go for it, right? This is what a neural network is, right? So then the real question is, okay, what we're trying to do is we're trying to solve this problem right here, right? Where we want to integrate scientific models with machine learning. And now this is what machine learning actually is, right? Machine learning is a tool for learning functions, right? So how do we piece these together? And the way that we're going to do this is we're going to say, let's think about models where we don't necessarily know the whole model, right? So here's a model of a Luck-Volterra model, right? So here's a Luck-Volterra model. So you have, so for example, that, okay, if I leave bunnies alone, X is the number of bunnies, then X prime grows as alpha X, right? So this basically says if I get the number of bunnies grows based off the number of bunnies because they, if you have more bunnies, you have more bunnies to reproduce, so you get exponential growth, right? And then you have another piece of the model that says if I have wolves, well, if I leave them all in a room together, I get less wolves over time because they eat each other, right? Very simple model, right? And then the question is, well, there's probably some interaction between rabbits and wolves. If I put them in the same room, there's probably something that happens. But my mother never really told me or wanted to complete the story about what happens when I stick a bunny in a room with a wolf, right? And so I don't necessarily know what goes here. I do know that there is some function, right? There's some function of X and Y, which if I knew what it was, I could write down and complete this model, right? But I can't do ODE modeling. I can't do controls. I can't do any of these applications without finding out what this model is, right? So instead of trying to figure out what this model is, what I could do is I can write down a thing that means any possible function, and then I can use that thing. Well, I mean, neural network means any possible function, right? So what I do is I stick a neural network here, and I say a neural network, and I take the first value out of there, and then go neural network, and I take the second value out of here. So this is a neural network that takes in two things and spits out two things, and it has a hidden layer size m in here. And as long as I make m large enough, then no matter what actually this function is here, this neural network can approximate that function that's out there. All I need to do is I need to find the weights of the model. I need to find the parameters that actually give me this representation. And how am I going to do this? Well, let me show you this in another case here, right? So this is actually a case where you're saying, okay, like I know Newtonian mechanics, right? So here's Newtonian mechanics in a rotating sphere or a rotating reference frame, right? So basically, what this comes from is you have two black holes, right? So if I have two black holes and they're going around each other, I assume that it's Newtonian mechanics. Turns out that Newtonian mechanics is wrong for this case because black holes, they're pretty big, right? And so things around relativity would actually be required. So I assume that I have a two-body problem given by Newtonian physics, but then there's these correction terms, this F1, F2, F3, F4, similar to how I wrote down over here. These are the outputs of a neural network. So I say, I know Newtonian mechanics, but let me learn how to correct my physics so that way I'm incorporating the relativistic effects. And what I'm going to do is from data, I can then say, hey, look, I have just a few pieces of data points over here. These are the black points. I'm going to learn from the data points, and then I'm going to extrapolate out, and I'm going to actually then predict what's going to happen in the future by what I've learned is not just missing parameters, but I've learned missing functions, right? These missing functions represented by the neural network. And if you go to docs.sciml.ai, you can find this exact example. Here's your discovering relativistic corrections of black hole dynamics. This is actually just a recreation of a paper turned into a tutorial where what you see here, I mean, if you walk through it, right, you create this model of, you put the neural network in there, and then you train it so that way you start from Newtonian mechanics, and then it learns how to do a small perturbation of the dynamics, and when you extrapolate it forward, it gives you the Lysygy pattern of that you'd expect from relativistic correction, right? What I was showing here with the Lock-Volterra model is you could do as well. So here's a case where first we generate out the data so that way we know the model. After we generate out the data, what we do is we build the version of the model that looks just like this, right? You have the neural networks thrown in with the code. I'm going to go quickly over this because I want to kind of go to the the meat and potatoes of this. But you train the neural network, right? This training process of the neural network is finding the weight matrices and the weight vectors such that this neural net the loss function is sufficiently small. Where here the loss function is, does the solution of the ODE go through the data, right? So I solve this ODE with the neural network inside of there, which I can do for any possible weights, right? Because it's just a function, right? I can always evaluate it. I might be evaluating it with the wrong weights, but I can get an ODE solution defined with these weights of the neural network. And then what I do is I take, I see how close I get to the data points. That's my loss function. The norm between the solution I get and my data points. And then what I do is I take the derivative of the ODE solution with respect to the neural network weights, and I use that to be able to gradient descent and optimize towards finding the neural network weights that then represent the function I don't know. And once I've done that, then I can actually say, hey, look, once I've trained it so that way I'm now that the ODE solution is going through the data points, I can actually plot it. So now this is actually then plotting what U of X and Y looks like, right? It's actually, well, it's plotting U of X and Y with respect to T, and it's actually showing you here, because again, I generated the data, it's showing you that I actually learned what that missing function is, right? Now, I have the function held in a very weird way. I have it held in terms of this. I don't have it in its original formulation, but I do have an object now that can stick points into that object, and it'll give me out, values that would be effectively this missing part of the function, right? And then what I can do here is I can say, okay, now that I have a representation of that function, I can do all sorts of things. I can do things like a global sensitivity analysis, find out what variables are in there, all sorts of things, right? So here what I'm showing, for example, is a sparse regression. Or what I'm going to do is I'm going to do a problem where it just says basically, z equals neural network of xy, find the simplest, h of xy such that z equals h of xy, right? So symbolic regression is just a problem of symbolically find a simpler function, right? So I can take the neural network and I can use this to build a data set, and then I can say, okay, here's the type of terms you're allowed to use to be able to build the function. Perform the symbolic regression on this, and it'll then say, aha, the most likely thing is that the missing function here is a quadratic function, and then it'll spit this out, and it actually will be able to generate the equations and then is able to extrapolate, right? Turns out that in this case, the way that we generated the equations was actually a quadratic function, so it found the analytical solution there. But yeah, so this is then shows you how you use this object, right? And there's many other examples inside of here. One's using a bioreactor, yada yada. But the key idea is you're using a neural network as a function that you don't know, and then you training it via the data of the solution process, right? And I have a whole bunch of different talks that go into this in a lot of detail. So I'll just point you to, for example, accurate and efficient physics-informed learning. There's about 2,000 citations on this stuff at this point that goes into, here's what it looks like in physics, here's what it looks like in earthquake-safe buildings, here's what it looks like in genomics, yada, yada, yada. So if you want to see the validations that it works not just on, for ODE models and general relativity, but that it works on your domain, this talk basically just walks through like 20 or 30 of those examples, if I remember correctly. So it's a nice, demonstration that, yeah, this is being used, and it is something that works across domains, right? But I just want to kind of just say that this is the mathematical idea behind it. This is how it works, and there's a bunch of applied validations that show that it works with Formula One cars and everything. I want to jump to the piece here that normally is behind the scenes, right? Now, inside, when you use the code, right, it basically just says you hit the training button, and then the training button gives you the neural network, and now magic is found. God has now descended and given you a neural network that's your missing function, right? And when we do this as applied software, that is totally fine, right? But now, as people who are mathematicians and want to learn the thing, the real question that you should have is, okay, you glossed really fast over the fact of how do I actually train this neural network, right? How do I actually find the weights that go in here? And it turns out that when you think about the scientific machine learning problem, right, choosing architectures, choosing the high-level things, like that's all very simple. You can do that as an undergrad, right? The real difficult part is actually doing the training process, right? This is where all the math and the numerical analysis comes into play. So let's dive into that a little bit, right? And the way that I'm going to dive into that is by using an example from climate modeling. So this is a nice example that came up when building neural network surrogates of a climate simulator. The key aspect here is that what we want to do is we want to approximate a column of ocean water, which is naturally a three-dimensional partial differential equation, right? So you have the Navier-Stokes equations, right? Navier-Stokes equations. And if you look at the Navier-Stokes equations, if you look at the Navier-Stokes equations, you'll see that you have naturally a three-dimensional object. How do you know that it's a three-dimensional object? Well, you have things like outer products and cross products cross products are not represented in lower dimensions, right? But we want to represent it in a lower dimension, right? We want to be able to take this object, which is a three-dimensional ocean model, which has all this kind of, chaotic stuff moving along. And what we want to do in this case is we want to say, I just want to know how heat flows up and down in the column. So I want to take a three-dimensional partial differential equation, and I want to approximate it by a one-dimensional partial differential equation. So how can I do that? Well, you can do the same idea, right? Where you can say, okay, I can start with an analytical idea where I want to take the average across these XY slices. I can compute the average by using an integral, yada, yada. The paper goes into a bit more details about the first step here. But what you get when you do this approximation is that to a first approximation, a one-dimensional heat flow is just diffusion and advection. To a second approximation, you need more things going on. So there's a whole Taylor series expansion of extra terms you need to have. And normally what you do in your physics class is just say, yeah, let me just chop those terms off. Diffusion advection is basically one-dimensional Navier-Stokes, right? It turns out that that's not actually correct, though. I mean, there are correction terms that would be there. You just need to do a huge expansion. So instead of making those zero, I'm just going to say there's a function that I don't know. Let me represent that function that I don't know as a neural network, right? So this is known as using a neural network closure approximation because there's a closure that's being done here. But skipping over some details there, right? We end up with a model that's effectively like before, right? It's not an ODE anymore, but it's a partial differential equation where there's a function that I don't know, and I want to learn the function that I don't know in order to get a better model of how one-dimensional heat flow in the ocean works, right? So what do I do? So then the question really just comes down to how do I train the neural network, right? Now, if I was doing machine learning, right, what I would do is I would get a data set, I get a data set of inputs, right, x, y, x, y, x, I, y, I, and then also have it matched with my outputs, right? So let me call my output zi, right? So I'd have a data set, right? And what I would do is I would then train the neural network such that, zi is approximately nn of xi, yi, right? And this is what you just do doing a normal method, right? So what you do is you, for example, write a cost function. So the cost function with respect to a function of the weights. I'm going to say that the weights, I'm just going to call this like W cost function with as a function of the weights is going to be something like, vert of nn of xi, yi minus zi. I'm going to do this where I sum over all my data set, right? So what I'm basically saying is find the weights. So find the weights W and B such that the inputs give you the outputs of the neural network, right? If I was doing normal machine learning, this is what I would do, right? Now, if the difficulty here is that I don't actually have my neural network directly, right? My data is not of the missing term of my model. The data is of the solution of the model with the neural network embedded in there, right? So what can you do? Well, first thing that you can think of is, well, I need to get this z sub I. So what I can do is I can maybe use my data, approximate x prime from the data, and after I approximate x prime, I can do x prime minus alpha x, right? And this gives me an approximation of what that needs to be, of what this term needs to be, right? So I can munge my data around such that I can, instead of having a time series, I put lines in my time series to approximate what the derivative is, and then if I subtract out this value from the derivative, I can build an approximation of what the missing part of the derivative is, and I can learn on that, right? And if you do that, then what happens is you get this problem in the learning process, right? The lines are diverging over time, and so what's effectively, well, actually this is a controls class, so this is a great place to ask this question, right? So what I'm effectively doing in another sense is I'm trying to have this neural network control the derivative, because my derivative is incorrect, right? I know my derivative function is incorrect. And so what I'm doing is I'm trying to put this neural network in there to learn a function to make the function be more correct, so that way my model matches my data, right? And what I'm seeing is that my derivative control causes a behavior that I have a drift that's growing over time. And so as a controls engineer, if I told you that you had a derivative control, only derivative control, and you had a growing drift in your model, what would your solution be? Like, what would you say I'm doing wrong?
You need the P and the I terms, right?
Yeah, I mean, if you're only controlling the derivative, then if you have errors, your errors will only grow, right? That you have a compounding error. In order to solve that problem, you actually need the I term. You need to be able to have an integral control as well, right? So this is one way to understand that if you just have this idea of I'm going to take my data set and massage it to get the derivatives, and then I'm going to train the neural network on the derivatives, you have this issue that errors at one point in your derivative and errors in the next point in the derivative can propagate, so that way you have a growing error. And so this ends up being a numerically unstable way to actually train this neural network, right? Another way to actually be able to understand it as well is that your simulation tool will actually introduce a bias, right? So you actually don't want the correct neural network here. You want the neural network such that when you add the bias of solving your partial differential equation or your ODE, they will cancel each other out such that you match the data set, right? Either way you think about it, it turns out that doing the natural process of finding a data set and training a neural network in isolation, training a neural network and then putting it into your simulator is not numerically stable. And so what do you need to do instead, right? What you need to do is effectively, again, the control solution is you need to, in order to have this error rejection property where you don't accumulate error from every single step going forwards, in order for a controller to not do that, you need to control the integral, right? And effectively what that means is that instead of correcting the derivative to be correct, you want to correct the integral of the solution to be correct, right? Which means, and so now let me write this down here, right? Instead, what you do is you want, so how do I make this be an integral control approach? What you do is you solve the ODE, PDE with the weights to get the time series x of t, y of t, and then take the difference between the predicted x of t and the data point x of I, right? So now your cost function in this case, your new cost function is to not take the neural network, right? But you actually take the x of t, right? Which is given to you by the weights of the neural network, right? If you change the weights of the neural network, then you get a different ODE and you'll get a different solution, right? So you want your loss function to be to solve the ODE with the neural network inside of there, and then take the data of the solution against take the data of the solution against the actual data point, right? Not through this transformation to derivative terms. And it turns out that if you do that, if you do this approach of my neural network needs to be correct, so that way the integral is corrected, then you actually get 2 to 3 orders of magnitude better fits, right? So it turns out that you will always pretty much see that this is actually called the collocation fitting method, and you can do collocation fitting. We have papers on this. Collocation fitting makes it so that way you get the derivatives correct. It is not as numerically stable, and it ends up having it ends up introducing other biases into the system. But this type of collocation can be a very fast way to do the training. So sometimes you do that to get a starting point before you then do the next phase, where the next phase is then embedding the simulation process into the loss function. And when you actually have the simulation process as part of the loss function, then you get about 2 to 3 orders of magnitude better fits, right?
Can we ask one question here?
Yeah, you can ask infinitely many questions.
Perfect. All right, so we have looked into the different types of integrators and collocation methods in control during the control class as way to discretize and put those inside the optimal control problem, right? So here you kind of talked about using the differential equations to get to the integrated solution. Is that something hidden inside of it, like when you're choosing either to use the Euler method, like forward Euler, backward Euler, or whatever method you're choosing? So is that step like just hidden here in your explanation?
Yeah, I mean, it's a bit hidden here. I'm just saying use some solver, right? Adaptive high order Runge-Kutta methods or PDF methods, yada, yada. Use some solver to get this, right? But actually the very next step is going to become important. So yeah, I'll get to that in a second there.
Perfect. Thank you.
Yeah, so that is the next. Well, so the next thing is, okay, now when you did the optimization part of your course, which I think you did, right? You always learn that you need to be able to get the partial C, partial W, right? You need to be able to get the gradients of your terms, right? So if I'm just partial W, right? So if you want to actually be able to do something like gradient descent or IP-opt, like interior point optimization, I saw that you have all these things in there, right? You always need to be able to calculate gradients and Jacobians of your cost function, right? The question is, how do you actually get the gradient of your cost function here, right? Well, naively, what happens by the chain rule, if you just write down the chain rule, right? What you get is well, there's no derivative here, and so what you're going to see is that you get, well, let's say that this is, let's just say that this is just the 2 norm, right? Let's differentiate it, right? What you're going to get is you're just going to say, okay, that this is going to be 2 times this plus fraction partial x partial w, right? And so this is what comes out, right? So then the real question is, what is partial xw partial x partial w, right? Because this is also like this x of t. How do I take the gradient of the solution of an ODE solve, right? That is a real question. How do I take the derivative of numerical solvers, right? Because the moment that I put a numerical solver inside of my loss function, by the chain rule, I have to take the derivative of a numerical solver, right? It doesn't matter if it's an ODE solver, a PDE solver, or whatnot. And it's hard because, like, so for example, let's kind of like write this down. So if I have the ODE, so if I have the ODE like u prime equals a times u, right? Then u of t is equal to the exponential of at, right, with u0 here, right? So then what I do is I go, okay, fraction, the derivative of u of t with respect to a, right, taking the derivative with respect to this parameter, the way that I would do this is I would look at the analytical solution and I just go, okay, so this is going to be u sub 0 times t exponential of at, right? Like if you know the analytical solution, then you can always take the derivative of it, right? But the whole issue about, the reason why you have ODE solvers and PD solvers is because you don't actually, you can't actually do that, right? You can't write down the analytical solution. In fact, in many cases, the analytical solution can never be written down, right? And so the question that you end up having to do is, how do I actually do this computation, right? So how can I calculate that derivative when all I have is a numerical method for approximating the solution, right? And that's the real tricky thing that comes into play here. And so really what this comes down to is, okay, if I want to stick neural networks and to be able to find missing functions, I can do all sorts of cool things. I have many other talks that goes into this detail that I'd recommend watching, especially the JulieCon 2023 one as well. But if you want to do all these cool things where you're learning the missing functions and auto-completing physics, right, you need to take the derivative of scientific models. So how do you take the derivative of scientific models? So this is what the meat and potatoes of this. I'm going to go quickly over this just so that way I can get to some of the other points in here. But the key aspect here is, okay, let's let g of up be a cost function of so let's let g of upt be the cost function of the ODE solution at a given time. Right, so we're going to say that we have instead of having a cost function that is globally, I'm going to basically say what is the cost function at every single time point. I'm going to call this g. I'm going to say I have a cost function at every single time point. This is g of t, right? And I'm going to basically then say I'm going to sum up my overall time points right here, right? Well, it can't really sum up overall time points because time is a continuous thing. And so you do the integral of this dt, right? So this is what this g of t is, right? It's an instantaneous cost function, right? So what I'm going to do is I'm going to say like my capital G of up. This is just a rewriting of c, right? This is just going to be the integral of g of u of t, right? Because again, the ODE solution over time, p t dt, right? From the initial point to the final point, right? So this is what I want to compute. I want to find out. So what I want to do is I want to take the derivative of this with respect to the parameters of my model, right? Where p is the parameters, and it's this alpha, this gamma, but it's also the weights of the neural network, right? So okay, so how do I do this? What I'm going to do is I'm going to introduce a Lagrange multiplier. There's a nice trick in this proof, right? So what I do here is I do, okay, I'm writing this such that my notation is u prime equals f of upt, right? And what this also means is that u prime minus f of upt is equal to 0, right? And so what I'm doing is I'm saying u prime is so this is 0, right? So I'm saying this is lambda star times 0, and so this is the mathematician's trick, right? I've just added in 0, so this is actually equal to just g of p, right? You'll see why I did this in a second, right? So okay, so what I'm going to do is I'm going to take the derivative of this expression with respect to p. So fraction. So okay, so fraction di dp is equal to now what I'm oh actually let me if g so g and I are equal to each other because I've only added 0 to this. So g and I are equal to each other. So the derivatives are equal to each other. But I want to take the derivative of this form instead. And you're going to see why as we go to the proof, right? And the way that I take this derivative is I just do the chain rule, right? So so how do I do the chain rule here? Oops. Opening up a bunch of stuff accidentally. How do I do the chain rule? Well, if my term before was it was this, right? If I had this term here, right? Then how do I take the derivative of this with respect to p? Well, what I do is I write this down as the derivative, right? So this is going to be partial g partial g partial u, and then this is fraction partial u partial p, right? Plus partial g partial p, right? That's just the chain rule written out, right? Why is this the chain rule written out? Well, because the solution to the ODE is actually a function of p, right? We kind of don't write that all the time, that our solution's a function not just of time, but also the parameters. And so if I need to do the chain rule, I need to do the partial with respect to the first term, and then that's non-zero, and do the partial with respect to the second term, right? dt, right? And then what I'm going to do is I'm going to write down, and the same thing, I do the chain rule on this right here. I do the chain rule on this right here. And if you want, there is, if you go to the 18337 notes, you go to the 18337 notes, you look on this, this goes through every single step of the derivation, and this YouTube video does the 2-hour version or whatnot of the derivation, or this one, right? So if you want to have like every little detail here written out, please go to that. But I'm going to show you effectively so the main thing that happens here is that the main thing that's going to happen here is that we're going to say, hey, look, this du dp is actually what we're looking for. So let's call s equal to du dp. Turns out by the chain rule that the derivative of u prime with respect to p is going to give you this s prime, and you do the same chain rule on f over here, right? So this gives you this term. And then we do something tricky, right? So what we want to do is we want to get rid of this s prime. We want to turn it back into another s. And so what we're going to do is we're going to use the integration by parts. We write down the whole expression. Again, if you want the slower version of this, the full 2-hour version, go check out the video. But after doing a bit of rearrangement and a bit of integration by parts, this is the expression that you get, right? And now you go, okay, how has that helped us, right? Now there's this lambda in here where the lambda just showed up in here because it's part of the zero. Like how the heck has this helped us, right? Here's the deal, right? Well, I can simplify this equation if I make this equation 0, right? So how can I make that equation 0? Well, this equation is 0 if lambda star prime minus this term plus this term is equal to 0, right? So what I do is I just require that. I just say, okay, this is how I calculate the derivative. So what I'm going to do is I'm going to require that this term is equal to 0. I'm going to require that lambda prime is equal to da, 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 da. And if that's 0, then all that I'm left is with here. And now the funny thing that happens is that this lambda, you know, like, okay, I use lambda adjoint. This is what the star means. This is the adjoint, right? So it's like the transpose, a complex transpose in a sense, right? What ends up happening in here is that this term is just an integral of whatever this lambda is. And so in order to calculate the derivative here, all I need to do is if I find lambda, then I find this. But it turns out that this itself is actually an ordinary differential equation, right? So if I solve this ordinary differential equation, I get lambda of t as a continuous object. And if I take the integral of that solution, then I get the derivative of the ODE. And now let me take one step back, right? So okay, well, what's the other thing here? The other thing here is I also have this term, right? If I want this term to be 0, then I can make that term be 0 if lambda star of capital T is equal to 0. So I'm just going to force that to be true. And so I simplified everything down by making this true. I zeroed a bunch of terms here. Now all I need to do is I need to take the integral of the lambda term. And you might be sitting there like, okay, you lost me. Like what's actually going on, right? Well, what's going on is this, right? If I want to calculate the derivative of a loss function in my simulator with respect to parameters, this is what it actually means, right? First, what I do is I solve this, my ODE, right? So first I solve this ODE, right? And then what I do is I solve this ODE. What is this ODE? This is this ODE that just kind of popped up in the derivation. Now, what do you mean I solve this ODE? Well, my initial condition is that I start at 0. So I start at 0 and I solve this going backwards, right? Because I have a final condition. My initial condition is the final point. And I solve this in reverse. And when I solve this ODE in reverse, I get lambda. Once I know lambda, I can actually stick lambda inside of this integral, and that gives me the derivative. And so you actually have this funny thing where the way to calculate the derivative of an ODE solver is first you solve your ODE, and you solve this other ODE going backwards. And basically the solution, you basically use the solution of this ODE going backwards to tell you what the derivative is. Again, and there's a lot of other things that ends up in here, right? And so I don't want to go into all copious amounts of details because it would take me forever. So again, check out the video that goes into then all the details of every single step here, right? But x equals. Oops, that's me talking. So okay. But the point here is that the way to calculate the derivative of an ODE solver is to solve a different ODE. To solve a different ODE, which gives you then the derivative. So okay.
It turns out, sorry, go ahead.
Yeah.
Just a very quick question, because one thing that kind of pops, and I'm not quite sure if that's correct or not, but it looks a lot like the Pythagorean maximum principle that we look when we're trying to kind of like solve trajectory optimization problems.
Yep, it is that. It is actually that object, right? The adjoint equation is the thing that pops out of this. And so yeah, the Pythagorean maximum principle, right, is a boundary value problem such that when it's satisfied, then you're satisfying certain properties of the derivative of what you're trying to achieve, right? It turns out that is actually that same adjoint equation is popping up out of there. The adjoint equation is a pretty natural object that shows up a lot of cases. But yeah. So the Pythagorean maximum principle is actually going to be the same equation. And it shows you then that using the same equation in a certain way gives you derivatives, and then from these derivatives you can do gradient descent. Then actually when this gradient is equal to 0, that's actually when you that point where it's equal to 0, you have another condition, and that's actually where the Pythagorean maximum principle takes place, right? But it shows that you can take one step back from it being a maximum principle to also being a way to be able to go towards the maximum via gradient descent. That makes sense?
Yeah, it does. And just very quick, I don't want to stop you too long. And it kind of, I imagine already that if you had other types of constraints in your problem that you wanted to kind of enforce there, that you would have to modify a little bit to kind of like this approach, right? Which I think you're going to get at the DAs, right?
Yeah. I mean, I won't get into DAEs today, but I mean, if you have a different algebraic equation, then you need to modify this equation a little bit, do initializations, yada, yada. But I think that the general point, though, that really you should kind of walk away with is the derivative to a numerical solver is to actually call that numerical solver. The derivative of an ODE solve is to do a different ODE solve. The derivative of an SDE solve is to do a different SDE solve. The derivative of a nonlinear solve, I mean, you can actually write it down as a linear solve, but effectively, in the derivative of numerical codes actually is a different numerical code that you run, where the interesting thing is that you actually use whatever function you're trying to solve for here, you use the function, you use the derivative of that function inside of that other call, right? Now, again, the other video goes into extra details about the fact that it turns out that this operation right here, you take the Jacobian, you take its transpose, and you multiply it by a vector. It turns out that this operation is exactly reverse mode automatic differentiation. So actually, another way of thinking about this is the way that you do reverse mode automatic differentiation of an ODE solve is you solve the ODE going forwards, and then you solve the ODE going backwards. What ODE do you actually solve going backwards is the reverse mode differentiation of f at every single step. So there's a relationship in there that's pretty deep. But again, that's the 4-hour version, right? The half-hour version of this derivation is derivative of an ODE gives you an ODE. You solve that ODE, that gives you derivatives, right? And so it's a really nice homework problem to work this out and do this one time yourself. But that's the key idea. But then it turns out that, then you had this question earlier about, okay, well, what about the numerical solvers? Do they matter? Yada, yada, yada. Turns out that this is, while you can numerically write this down, turns out that there's a lot of issues here, right? So first of all, for example, when I write down this equation here, right? When I write down this equation, I'm saying, calculate the Jacobian of f at with respect to u at that time point, right? So as I'm going backwards in time, I want to calculate the Jacobian of my original function with respect to u, where u is the ODE that I solve for going forwards, right? So how do I actually have u of t, right? There's a few ways you can do that, right? When you solve going forwards, you can actually store the entire u of t as a dense interpolation object, right? That's going to take a lot of memory, right? And so generally you don't want to do that. There's some fancy checkpointing schemes that you can do, right? But the funny thing is that there's actually some other papers that say, well, you can skip it, right? So so you need, so what's the problem? So the problem is that you need to have u of t while you solve for lambda of t, right? So you have that u prime is given as f of u upt, and then you have that lambda prime is equal to, I mean, effectively, I'm going to write it down the simple way. I'm going to say that this is partial f, partial f, partial u of t lambda, right? Well, this has a transpose in here, right? So this is effectively what it is. You just have the Jacobian transpose lambda, and you're just solving this in reverse. So there's an extra term in here which corrects for there's something in the loss function, but it's usually 0, yada, 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 right? This is the simplification, right? So now the question is, okay, but you solve this going forwards, and you're solving this ODE in reverse, right? How do you actually, well, if you stored an interpolation for all of the u, what you can do is inside of the ODE that you write here, you can say, hey, at this time point, interpolate from that ODE solution, grab it, now use that value, calculate the Jacobian, transpose it, and multiply by lambda, right? But the issue is that that means that you have to store this entire dense vector, right? And so what you see in the machine learning literature, they actually say, hey, look, there's actually this property that if you have u prime equals f going forwards, then in reverse, the reverse ODE is just given by u prime equals minus f. You can solve that in reverse, where now, what is your initial condition? Well, your initial condition is just the end of your ODE solve, right? And so this is the reversibility trick, and you actually find this, for example, like in the paper Neural Ordinary Differential Equations. It won an award in 2018, where it said, if you do this and then you do one other trick, right? So what's this other trick? Well, the other trick is if I want to calculate the integral of f of t dt with an ODE solver, how do I do that, right? How do you figure this out? Well, let's actually just write down Euler's method with this, right? So un equals un plus f of t sub n, right? So this is Euler's method. So let's actually just write this out. So like u1 is equal to u0 plus f of t0. So then u2 is equal to u sub 1 plus f of t1, but we know what u of 1 is, right? So we can actually just plug this in here. Actually, I forgot that there's going to be there's a delta t here, right? Right, for the Euler's method, right? So what does this mean? Well, you can see how this continues out. U sub n is equal to u sub 0 plus delta t summation of f of t sub I, right? Does this actually look very familiar to anyone? This term right here?
Yeah, we've walked to on the integrators, and that's forward Euler, right?
Yeah. So this is the forward Euler method written out, right? Well, okay. So let me actually. Oh, I think I forgot to say a step. So let's solve u prime equals f of t using forward Euler, right? If we do this with forward Euler, what you actually see is that this is what you get out, right? And if I wanted to, if I approximate, this integral via trapezoidal method, then what I have is this, right? I do the sum over I have a weight sub I, and then I have f of t sub I, right? Now, if I do trapezoidal method, the weight is delta t, right? It's the weight between these, right? So if I want to approximate an integral, then I use the trapezoidal method. This is what I have. if I solve this ODE with forward Euler, this is what I get as my term. So so there's actually a quick, like little lemma here, which is that if you solve this ODE, so if you solve an ODE with an explicit function, such that you would just assume that u of 0 is equal to 0, then u of t is equal to the integral, right? So you can always use an ODE solver. You can use a numerical ODE solver to calculate integrals, right? So what you can do here is you can say, hey, look, I need to calculate the integral, right? So dg dp is actually then just given by right? It's given by this integral of is given by the integral of fraction partial f partial u, or no, partial f partial p transpose lambda, right? That's what this proof says, right? But if I want to calculate this integral, right, what I can do is I can just say mu is equal to this thing right here, where what I have is that mu of 0 is equal to 0, and what this means is that if I solve this ODE all going in reverse, then mu of well, actually going in reverse, right? So mu of t is equal to 0, and also have that lambda t is equal to 0, right? From the adjoint equation, then mu of 0 is actually equal to dg dp, right? Again, the whole derivation is slower in the full course notes, but the idea here is that instead of actually calculating this integral, I can calculate this integral by using this trick that integrals can be calculated via ODE solvers, right? All I do is I just put the integrand as the term in the differential equation, and then the end point of the ODE is actually the integral solution, right? And so if I want to calculate this integral, I can just write down this ODE instead, right? And solve this ODE. And why would I do that? Well, if I do that, what? Yep.
No question.
Yeah. So why would I do that? Well, I do that because I need to know what lambda is, and lambda is given by this ODE. So I can actually solve these two ODEs at the same time. And if I also know that, and if I also allow for this trick that, u prime equals minus f is the same ODE going reverse, I can solve all three of these ODEs at the same time, and then mu of 0 is equal to the derivative of the loss function, right? So what this means is that, what is, how do I calculate the derivative easily, right? You do this. You first solve u prime is equal to f of upt, then solve this system of equations, right? And then mu of 0 is equal to the gradient that you wanted, dg dp, which is the gradient of the cost function, right? And you do the whole derivation, that's what you see. You solve this ODE going forwards, you solve this ODE in reverse, and you get the derivative out. There's a paper that wrote, that's how you do it. You solve this ODE in reverse, you solve this augmented ODE in reverse, boom, you get your derivative. What can go wrong, right? Well, it turns out that this idea that u prime equals f going forwards implies that u prime equals minus f in reverse. It's true in a mathematical sense, but it's not numerically stable. What's the case to show that it's not numerically stable? Use the discretization of the advection equation. Right? So if you've done your linear PDEs course, you know that when you're solving, let's say we have an advection equation where the two solutions go into the right like this, right? You know that you can take this term and you can discretize it in two ways, right? You can either do the upwinding version or you can do the downwinding version. But since you know that your analytical solution is moving to the right, your update equation better use the value from the left because this value will be the analytical solution the next term, right? So one of these is correct, the other is unconditionally unstable, right? I mean, you could use your standard von Neumann analysis, the thing that you do in your linear PDEs course to show you that, yeah, upwinding is stable, downwinding is unconditionally unstable, right? The issue here is that this is actually a non-reversible ODE solve, right? So if you solve this ODE for going forwards using the upwinding method, and then if you just naively flip the term and you solve this ODE in reverse, what you actually get is that the reverse solve is unconditionally unstable because it's now doing downwinding of the advection equation in the reverse direction, right? this is actually something where you can actually see in a lot of other cases, right? So for example, if you solve this ODE, just a linear ODE going forwards, and then you just say, okay, now solve the minus lambda u going in reverse, right? If you have lambda as close to 0, then you actually, if lambda is equal to 0, you're perfect. If your lambda is close to 0, you don't have very much error. But if lambda is negative, you actually get exponential growth in the numerical error of this solve. And the reason is because Euler's method will just be compounding and compounding all the error that it gets as it goes in reverse. So this is something that is mathematically true, but but is numerically unstable. And so this idea of, oh, the way to be able to calculate your derivative is you just solve this set of 3 ODEs together in reverse, and then now you get the derivative, right? This is actually what's implemented in PyTorch as the way, if you go to Torch IfEQ, it's implemented in PyTorch. So if you stick in one of these ODEs that are non-reversible, you actually get a gradient that it says is infinite, which is going to make it very difficult to train your neural network, because it's just going to keep on saying your derivative is infinite, even though it's finite, right? And so what this really shows you is that, just like with ODEs, right, how you just kind of say, oh, here is a way to approximate the ODE. Euler's method is a way to approximate the ODE. Turns out there's many ways to approximate the ODE, because it's a numerically difficult problem, and some are more numerically stable, some are faster, some are slower, right? This method of putting them all together is actually the least memory way of doing it. It's O of 1 in memory, but it is not numerically stable. And so there's all these different tricks and stuff that you can start to do. This becomes its own discussion, right? And actually, differentiable programming review. We actually just got a review that was accepted into SciAm review. So now it's going to be a SciAm review paper. It's going to go around pretty soon, but it's already on arXiv if you want to see it. This goes into detail about the many different ways of moving around how you write down and solve the adjoint equation, such that you get very different methods, where what I showed you right there is the backsolve adjoint method, which has poor numerical stability, but it has good performance, it has good good memory. But then there's many different ways that you can tweak this around, right? So just like solving ODEs has different methods, it turns out that calculating derivatives has many, many different methods, because there's many different approximations that you do, right? Now you might go, okay, why do I need to care about all this? Programming languages have something called automatic differentiation built in, right? So why don't I just call automatic differentiation of the solver? Turns out that this is actually a very interesting question as well, right? And to show what goes wrong, I'm going to use JAX, because we've actually fixed it within the Julia space. And I'm going to describe a little bit here. So here's just a simple ODE, right? So I'm just writing down the ODE. I'm just saying that, x prime is equal to alpha y minus x, and then y prime is equal to beta x minus y, right? And my initial conditions is x of 0 equals y of 0 is equal to 1, right? So it's a very simple ODE. In fact, the solution is continuous. But if you take the derivative of the ODEs with respect to its initial condition, changing the initial condition by a little bit no longer makes it have a constant solution, and so that derivative is actually non-trivial. So this is an ODE for which the solving process is trivial, but its derivative process is non-trivial, right? It turns out that this is a bad case for automatic differentiation. So why is this the case? Well, I can actually say this is a linear ODE, so I can actually write down the analytical solution to the ODE. So I actually know the analytical solution, and I know the analytical derivative, right? So what I'm going to do now is I'm going to ask the Python library, right, JAX, I'm going to ask it for what the derivative of the ODE is, right? Well, first I'm going to do this with finite differencing. So what I do is I write a function here that takes in initial conditions, or it takes in the initial conditions, right? And then it solves the ODE with those initial conditions, and it spits out a value, right? So this is basically just kind of like a loss function of sorts. It's going to spit out the final value as a value, right? So I want to take the derivative of the ODE solution with respect to its initial condition. Simplest way to do that is finite differences, right? So I take the finite difference here, where I perturb the initial condition a little bit, take the difference, divide by the perturbation amount. I get 1101373. The analytical derivative is actually very close to that, and so finite differences wise, this actually gets pretty decent, right? So now let me do automatic differentiation on the solver here. When I do automatic differentiation on the solver here, it gives me 3755. It gives you greater than 60% error. In fact, as I change around the tolerances of the ODE solver, it does not change the solution at all. It's just so it turns out that this is actually a case where standard automatic differentiation implemented correctly does not converge to the correct solution in this case. Which I think that this kind of confuses some people because you think automatic differentiation is floating point accurate in every step. Why would this go wrong? Well, I'll show you. And the way that we found this out is actually we make it so that way we don't do automatic differentiation correctly in Julia, specifically so that way we can calculate these derivatives correctly. So if you go to Julia and you take the same ODE, you ask it for its derivatives, you find that it's all 113, 110, 13, We all get this correct very closely. So what are we doing differently, right? So what is going on here? Why can automatic differentiation give an incorrect value? Again, this is something where if I want to have the whole 4-hour version to do the whole derivation, but the key idea here is that automatic differentiation is actually doing an approach of So okay, what was the quickest way of doing this? Yeah, I won't have enough time to do this whole explanation, right? But the idea is that automatic differentiation of a solver, what it's actually going to do is it's going to take every single step of your code and turn it into a code that's effectively working on a higher dimensional object, right? So instead of working on just a floating point number, it turns it into something that's working on a floating point number plus another thing. Think about it almost like it's a complex number where there's a value term and a derivative term. It's a two-dimensional object, right? And so what it's going to do, if you actually look at what automatic differentiation does on Euler's method, if you take Euler's method and you stick in a dual number, so a dual number is equivalent to doing automatic differentiation, then what you can actually see what happens with automatic differentiation. So automatic differentiation of a code that does Euler's method takes a thing that does Euler's method and it turns it into something that solves two ODEs at the same time. Right, solves this ODE and it solves this ODE at the same time. It turns out that is very well motivated because, okay, so how can I calculate the derivative of an ODE using the forward mode? Right, if I take u prime equals f of upt, right, and then what I can do is I can do ddp of both sides, so I can do ddp of du dt is equal to ddp of f of upt, right? Let me then just do the chain rule here. Well, first of all, I'm going to swap limits unapologetically because the solutions of ODEs are smooth, right? So if I do that, you see that this is equivalent to ddp prime, right? And then I just do the chain rule here, right? So what's the chain rule here? This is fraction partial f partial u, and then this is partial u partial p plus partial f partial p. This is partial f partial p, right? And so this is what happens if you take the derivative of both sides of this ODE. It turns out this is actually something that's known as the forward sensitivity equations, right? So the reason why you don't necessarily want to use this to calculate your derivative is because it actually has quadratic growth. So what I showed before requires solving O of n plus p equations, while this takes O of n times p equations. So it's basically, this is the forward mode version, and the other was the reverse mode version, right? And so as you get really large equations, this one is slower, yada, yada, yada. But if you actually look at what happens if you do forward mode automatic differentiation of Euler's method, it actually gives you Euler's method approximation to this system of equations, to the system of equations that you'd solve for the forward sensitivity equations. So it turns out that automatic differentiation basically takes ODE solvers for an equation and turns them into a new ODE solver. And that new ODE solver, if you set dt equal to 0, is approximating this set of equations, which is truly the derivative, right? I just derived it for you in 2 seconds, right? So why is this potentially an issue, right? The reason why this is an issue is because the way that automatic differentiation works is it'll always take the same branches through your code, which means that you will have chosen time steps, h's, delta t's, such that your original process, this process, is numerically stable. But when you do automatic differentiation, it's going to generate a solver for this set of equations. And it's possible that that your ODE solver is not actually numerically stable on this equation, even though it was numerically stable on this equation. In fact, this is a great case to identify this because, again, the original equation, right, the original ODE is just a constant, right? Well, so this is just a constant, right? This is just u prime equals 0. And then this is something that's just an intense equation. And so what ends up happening is the time step choices that are stable here, an adaptive ODE solver will take really big time steps, and then automatic differentiation will be pushing things through this term where the time steps are large enough such that it's not numerically stable anymore. And so you have this divergence in the derivative. And that's actually why JAX is computing the wrong values here, because its time stepping routine is incorrect, right? I give a talk where then I talk about how you can actually use, you can then do automatic differentiation incorrectly by making your time stepping algorithm take into account the automatic differentiation process. And that's how we've actually corrected it within the Julia library, right? So the weird thing that happens here is that if you solve using the Julia solvers, the number of time steps it takes when not doing automatic differentiation is different than the amount that happens when you do automatic differentiation. And this is done to be able to ensure that we have error control over the generated equation, the pseudo-generated equation that's in there. So that way we guarantee that that's two tolerance as well. Again, if you want to see this in a lot more detail, I think that I go through the derivation in a lot of detail in this scientific machine learning wrong, right? So if you look at automatic differentiation in scientific machine learning, what can go wrong?
Well, there's ways.
Yeah, this does a whole derivation of the whole thing, a whole whiteboard version of how automatic differentiation works and how this ends up being non-convergent. So I'll leave it there because I'm running out of time. But the core point is that basically scientific machine learning comes into this thing of like, okay, what you're doing with scientific machine learning is you're sticking neural networks into scientific models to be able to have a function approximator and get all those properties of machine learning while still having the goodness of scientific models, right? And it turns out that if you do that, a lot of software, is nice and easy to use, but the reason why it's become easier to use is because the core numerical analysis problem is how to calculate derivatives of solvers effectively. Because it turns out that it's something that's very numerically unstable. And so just like how you just say, oh, you can use Euler's method to calculate, to approximate ODE solutions, it becomes this whole thing of like, well, Euler's method is not good for this. You need to use implicit method sometimes. It turns out that the whole idea of how do you calculate derivatives of numerical solvers then explodes into its own domain of, oh, here's all the different ways of solving them. Some of them have different performance characteristics, memory characteristics, and there's always trade-offs between them. And so the core of scientific machine learning as a mathematical discipline and then is about the numerical analysis of differentiable programming. And I'll stop there because I'm out of time, but hopefully that gives you a nice overview into, you know a bit now. Go to this tutorial, stick neural networks in there, you can automatically discover missing physics. Cool, all the software works, but if you're interested in the actual, like, okay, what's the math class about? The math class is then going into numerical stability of derivative calculations. So yeah, hopefully that gives you a nice overview. Again, that's the 1 hour version. I give like, I usually do that talk as like, 4 or 5 lectures where each lecture is as long as this, but hopefully that gives you a nice overview.
Perfect. Let's thank our speaker. Thank you very much, Chris. That was very nice and a very nice introduction to now the second part of the course, which kind of like we want to explore these themes. I have a few questions, but I'm going to open, if that's okay with you, to kind of like the other students, if they have some questions. If not, I'll bug you with a few questions of my own.
Oh yeah, totally fine. Happy to take any questions. I'll probably be setting up for little things here, but I'll still be answering, so don't worry.
Perfect. And whenever you want to hop off, just let me know, and then we'll end there. And we'll keep it offline.
No worries. I realize that there's a bus I got to catch, and but I mean, I'm just going to jump on my phone here, so it should be fine. But yeah, ask the questions away. Yeah.
Okay, let's do perhaps one or two questions, and then we will let Chris go, and then so that it doesn't become too long. Someone wants to go first? Okay, I'll do my question then. So at the end, you kind of showed us, or you hinted at that it's very important to kind of think about not only which integrator we're going to use for like the forward step and simulating our systems, but also how we're going to take the gradients over those, right? And I remember you have had a few posts on those topics saying it's not always clear which one is best if you're choosing explicit or implicit and all those things, right? So my question, we didn't dive super deep into those subjects, but one thing that we did, let me admit you here. One thing that we did hear a lot was there are some methods that seem to be very, can you hear us still? It's muted. Oh, you're muted.
Yep, I still, yep.
Oh, perfect. Yeah. So there are some methods like Runge-Kutta methods and some collocation methods that seem to be much easier for us to choose a even fixed time step, right? For it to be stable. Do the same things that would happen in something like forward Euler, that it's known to be very easily become unstable. Does that happen as well with other explicit methods like Runge-Kutta? When you're differentiating?
Yeah, to an extent. So I mean, I will issue a small correction. I mean, I don't know if you saw that I had a blog post fairly recently on the fact that implicit methods are not always more stable, right? So it turns out it's just depending on how you measure things. Implicit methods can either be more accurate or less accurate. In fact, they always dampen oscillation. So on oscillatory problems, they're less accurate than even explicit Euler, right? So, you know, like I normally like to say that instead of saying like, oh, you know, implicit methods are more stable, I'd instead say for certain types of problems they're more appropriate, for other types of problems they're less appropriate, right? And similarly, you get the same property for these different derivatives, right? So for problems where you have reversibility, the part where I said, oh, you do this reversible thing and everything, will actually be the most memory efficient, most compute efficient way of doing it. So do it. That's the best method to do. It's just when you get to a case which is non-reversible, now it's numerically unstable. So you don't want to do that, right? And you end up having different numerical stability properties, you know, that can happen in different cases. So you can say, okay, if you have a symplectic ODE, then this method ends up being this method of calculating the adjoint is more stable. And if you have a ODE that's going to a steady state, then this one's more stable. And it ends up having all these kind of if, the same way that you have all those ifs with ODEs as well.
Perfect. And I imagine your symbolic reasoning behind SML of scientific machine learning helps us decide which ones to use that depending on our system, right? We might have lost Chris.
Oh yeah, sorry. I was switching off of Wi-Fi and yeah. So ask the question again.
I imagine the symbolic reasoning behind scientific machine learning framework helps us perhaps in a direction on how to choose automatically using those ifs to choose the correct approach for solving our problem, right?
To an extent. Yeah, I mean, like the SciML infrastructure, we've set up a automatic choice algorithm that tries to do the right thing, but I can definitely tell you edge cases of like, it doesn't really give you the right one here and here. I mean, because again, it could be so deep into the properties of the equation. So kind of like with ODE solvers, right? You could give someone some like, oh, these tend to be the good choices, right? But there's always violations of that. And so, you know, there's still a lot of work to be done. That's the way that I put it.
Perfect. Thank you very much, Chris. Let's thank again, and I'll allow you to go through your bus.
Yeah, no worries. Thank you. And thanks for being able to switch weeks here because, yeah, I've been in the middle of traveling and whatnot. So it's I was able to just slide this in right at this time.
We are very glad you came. Thank you very much and have a great end of your day.
Alrighty. Thank you so much.
Bye.